Okay, so these problems are going to be the last of our surface questions, okay, or looking specifically at surfaces. So now we're going to look at, so all the previous questions assumed that our surface was horizontal or flat, a table, ground, and so forth. So now what will happen is sometimes you're going to encounter a surface that will be inclined, right? And so it'll be a ramp, okay? And so we call these inclined plane problems, right? And so here's the physical picture of what will be happening. How you draw your incline doesn't matter. I go back and forth where I put the tip to the right or tip to the left. It doesn't matter, okay? Because when you actually do these problems, and so this would be the angle of incline, okay? When you do these problems, the main strategy here is that you must turn your coordinate axis, right? So you got to turn your positive axis to match the incline in some way, okay? And typically what you're going to do is you're going to put positive in the direction of the motion. And I'm going to say assumed motion, okay? Because sometimes you may assume the motion to be one thing, but your numbers work out to be the opposite thing, okay? Now, the reason why we do this is because we want multiple forces acting in a single direction. And if we turn our axis, that means only one force, the weight, will be in two directions as opposed to be in one direction. Okay? So to find the horizontal component of the weight, you're going to do FGX is going to be FG or mg sine theta. Now, I know sometimes this is an area where students will be like, wait a minute, but it's always x goes to cosine, y goes to sine. The difference here in the triangle is that we know the vertical angle, not the horizontal angle. Okay. Yes, we know the angle of incline is measured from the horizontal, but your weight vector looks like this, because it always goes straight down, which means when I break up the weight into components, now that my coordinate system is going to be changed, right? This is the angle I know, and these two angles are the same, but it's the vertical angle I know, which now puts the x direction as the opposite side and the y direction as the adjacent side. And so to find the y component, or the vertical component, you're going to do FG cosine theta, or mg cosine theta, okay? And so just like all the other surfaces, inclined planes can really, can experience friction, not experience friction, okay? Objects, on inclined planes can be accelerated, cannot be accelerated. So you just have to figure out, it's situation to situation, right? It's based on what the problem says, right? It's not, so Newton's second law questions, I can't just tell you memorize this equation, memorize that equation. I can't, because I can always change one little thing, okay? So here's our first example. It says a child of mass m and an adult of mass 4m simultaneously start from the top of a water slide that has a downward slope of 30 degrees relative to the horizontal. Which person reaches the bottom first? Okay, so this is a conceptual based question. I know it's like, but wait, there's numbers, okay? But we're calling it conceptual based because, right, we're just trying to answer that question of who reaches the bottom first, okay? And so here's our free body diagram. Our free body diagram is going to be the same for everybody, okay? And so we're going to do, and so so a water slide is typically frictionless. So we're going to do weight, normal, okay? And so what we're going to see is, so that's going to be our free body diagram for both. And so so if we break this up, this is our y, FGY, this is our FGX, And the only force that accelerates or that brings the person down, whether it be a kid or the child or the adult, is going to be the X component of the weight, because we have no friction. We don't have to worry about the vertical piece, okay? And so what that's going to look like, all right, is we're going to do sum our forces in each direction, right? And so we're going to do sum of the forces in the y direction equals 0, Fn minus Fgy equals 0, right? Again, Fn equals Fgy. Don't classify this as part of the 10% because technically we are still equaling this to the weight. So the 3 mg cosine theta will be our normal force, okay? And so then we're going to do the sum of the forces in the x direction, right? And so what we're going to really try to find is what is so the acceleration is what's really going to tell us what, who's going to go down first, okay? And so the only force we would have, and here's what we're going to put our positive down the incline, right? Our positive x is going to be down the incline because that's the way they're going to slide. So that puts Fgx going to the positive direction. So we get Fgx equals max. In fact, we can just get rid of the x because it's the only acceleration we have. Well, Fgx is mg cosine theta, right? And so it's going to be max, right? And there again, I put, max or ax, okay? But I want you to see something that happens here. Notice what happens. So this, I'm not looking for the child, let's do it for the child, right? So the child has a mass m, cancels out. So we find that the child's acceleration down the incline is g cosine theta. Okay, keep that in mind. Now let's go over and do, so this is for the child. I feel like I'm talking about the Mandalorian, right? The child. We all know the child as Baby Yoda. Okay, and so now we'll do the adult, right? And so y direction, again, equals 0. And I'm going to fly through this a little bit. I'm not going to explain as much because this part is always the same. All right, so Fn equals Fgy, which equals mg cosine theta. Sorry, I messed up over there. Hold on, let me go back over here to our Baby Yoda. This should be sine, not cosine, because in the x direction it's sine. So the acceleration is g sine theta. I apologize for that. And so then we do the sum of the forces in the x direction equals, max, right? Because the adult's accelerating, or ma, right? And so then I now plug in, so the only force again is Fgx. So ma equals ma, and then we have mg cosine, or did it again. So mg sine theta equals ma, right? So they have a mass of 3m, right? So 3m times g sine theta equals 3m times a. Well, look what happens. 3 cancels, m cancels. So what's the acceleration of the adult down the incline? The same thing, right? So who is going to get to the bottom first? They're going to arrive at the same time. Why? Because their accelerations are the same. Okay? Now, remember, this assumes perfect physics conditions, right? And so there are other factors that go in, child and adult. If you go try this at home, you're probably not going to end up with the same result, okay? All right, next question says a loaded penguin sled weighing 80 newtons rests on a plane inclined at an angle of 20 degrees to the horizontal. Between the sled and the plane, the coefficient of static friction is 0.25 and the coefficient of kinetic friction is 0.15. A, what is the force that would be needed to be exerted to prevent the sled from slipping? And then what is the minimum force that will start the sled moving up the plane? And what force is required to move the sled up the plane at a constant velocity? Okay, I'm going to split this into thirds, kind of, ish, right? And so I'm going to do part A. guys, remember, draw, sum, solve. So here's, so our physical picture is essentially something on an inclined plane. And so our free body diagram would look like this. So we have the weight of the sled down. We have the normal force perpendicular to the surface. We have this applied force, which is what we're looking for. Now, when you see this talk about keep it from slipping, that means at this point in time, we don't want the sled to go down the incline. So we don't want a downward motion, which means my friction would actually be up the incline, okay? And again, because I want my motion to be up, I'm going to call positive up the incline, okay? It's a little weird to see friction going in the same direction as the force, but this is that idea that of slipping. We don't want the object to slip down the incline, okay? And so now we do our x and y, okay? Sum of the forces in the y direction is MAY. I'm sorry, it's going to be 0 because we're not accelerating through the incline or off the incline. And so we're going to have Fn minus Fgy equals 0. So Fn equals Fgy, which equals mg. Did it again. I always get these two mixed up in this scenario. Mg cosine theta. Okay. And then over here, let me erase that big, because really we're done with the y direction. So I'm going to kind of rearrange my chart here a little bit to give me more space for the x direction. So now we're going to solve the x direction. Okay. Now slipping means we don't want it to accelerate. So we're going to do sum of the force in the x direction is going to be 0. And so what we have is we have the force we're looking for, and we'll call it Fa, right? So applied force plus friction, which is very rare that happens, excuse me, minus Fgx equals 0, okay? And so now I'm just going to do algebra to solve for Fa. So Fa is going to equal Fgx minus friction, right? Fgx is mg sine theta. F is mu Fn, but I figured out mu Fn was mg cosine theta. So it's going to be mg sine theta minus mu mg cosine theta. Okay, I'm just going to pan up a little bit for right now because I'm bending over. And so I can do a little cleaning up here, right? mg times sine theta minus mu cosine theta. Okay, and then my numbers are going to be 80, right? Now they tell me 80 Newton weight, right? So I don't have to do anything past that. And it's a 20-degree angle. And because we're looking at static, right, we're going to do 0.25 times cosine of 20. And we're going to plug it into our calculator, and we're going to find that this force that we have to apply is 8.57 newtons. So it's like if I'm holding the sled, I only have to apply 8.57 newtons, which is roughly less than a kilogram. Okay. All right. Now for the next one, we're going to find what is the minimum force that will start the sled moving. Okay. Again, draw, sum, solve. I'm going to keep telling you guys that for a while. Okay, draw, sum, solve. Okay, so here's our normal force, here's our weight, here's our applied force. Now, here we want to go, right, our friction, now we want to go, our motion to go up the incline, which means now our friction is going to go down the incline. That's the difference between A and B. In fact, it's the same free body diagram for C. The only difference is we change our subscript. This will be, B will be static, C will be kinetic. So what happens in B and C, you're going to get the same equation. You're just going to use the different coefficients. Okay, so here's our xy. So sum of the forces in the y direction equals 0, right? Fn minus Fgy equals 0. Fn equals Fgy. Fn equals mg cosine theta, right? Typical, right? That's typically what happens when we have these problems, okay? So we got the sum of the forces in the x direction equals 0. Okay, remember when we're doing anything with static friction, it's always going to equal 0. So we're going to Fa minus Fs equals 0. Okay, and that's going to tell us that the applied force is going to equal the friction force. And I feel like I'm missing a force. I am. Thank you for catching that. You're welcome. So let me. Okay, so it's going to be minus Fgx minus Fs equals 0. I forgot the x component of the weight. Remember, we're on an incline. So Fa is going to be Fgx plus Fs. Okay, you can see we're going to get the same look as we had in part A, but the difference is it's going to be a plus sign instead of a minus sign. So this is going to be mg sine theta plus mu Fn. Well, there's Fn again, it's mu cosine theta. So we're going to get Fa equals mg times sine theta plus mu cosine theta. So there's your difference again, right? In part A, it was a minus sign. In part B, it's a plus sign. Okay? And so now we're just going to do Fa equals 80 times sine 20 plus 0.25 cosine 20. All right? And so that's going to end up being, well, let me plug in the calculator. So 80 times sine 20 plus 0.25 times cosine 20, and that's going to be 46.2 newtons. Okay, so this is the amount of force I have to apply to get it to go, begin moving on the incline. Okay, now for C, guys, it's going to be the same solving and all that. The only difference is when we get to the point of plugging in, all right, we're still going to have mg times sine theta plus mu cosine theta. It's just that now we're moving. This is now going to be kinetic friction, not static friction. Okay, so it's going to be Fa equals 80 times sine 20 plus 0.15 cosine 20, because it tells us our kinetic friction is 0.15. So I'm going to go back to my calculator, plug all that in. And so our friction, or our applied force, is going to be 38.6 newtons. Okay, so you can see, does that hold true? Well, Fa focuses on kinetic, and that should be less than our static friction, and it is. Okay. Now, the shifting in the next video, I'll give you a little preview, is that we're going to now start talking about when objects are connected by ropes, strings, or they're simply touching. Okay.